sorry. For current source, we don't know the real voltage of this one, so we need to suppose one, right? And then we use this one, we use this unknown voltage to write our KVL equations. Then we add one more equations for it, x equal to I2 minus I1. And I add one more constraint equation for voltage of CCCS and mesh current. Ix, we know the control signal is Ix, right? So we need to add one more equation for Ix. This is the case 2, right? Okay. Do we see this example in our last course? I talked about this. Do I? Okay.
I use this backlog here use this Kreml, but I use this matrix. X equal I use X equal B, so I find X equal I1 equal to transfer A.
You can say a message, right? Okay, this one is a practice, right? Just I give you 5 minutes to try this example, okay? Try this practice. 5 minutes. Just look at this one. And before we start, we can do a short analysis for it, right? So, this one we have 4 resistance, 1 voltage source, and another. What is this one? What is this one?
Dependent source.
What kind of dependent source?
Voltage.
It's current
Current controlled
voltage source, right? So, you're trying to solve this one. Okay. What method should we use?
Loop, mesh.
I think for me, I will use mesh currents because we really have 1, 2, 3 meshes, but we have 1, 2, 3, 4 nodes.
Yeah.
And if you use node method, if you use a node voltage method, it's okay, because we have 4 minus 1, 3 equations as well. So it's up to you. You can use any one. Just try it. I think for me, I use mesh current method here. Is it mesh current? Just try it. And here, I use the shortcut way here. Do you remember how to write the shortcut? Remember? For my method, we can use the mesh current, and there is that I1, I2, and I3 as a feature. Okay. Do you still remember the shortcut method?
But for me, short better than formally shortcut is current.
For anybody, the shortcut is a very useful way. one more thing, the supervisor, Miss Peng, she told me our examination will be in the next week on Saturday at 7 p.m. to 9 p.m. Examination. So I negotiated with her, and she said for our course we must have an examination. All your classmates, not only your guys. And I give you the paper, the exam paper at 7 o'clock, and then you and your classmates should finish those questions in 2 hours and send the result back to my email. But I'm not sure if he will come here or just stay at home. So I need to talk with her. Okay.
I think so. This grade is 24. Online.
Yeah. So she said we must have an examination. So it is maybe no possible to just do an assignment and then class.
Some days ago we talked with her and she said it's up to teacher.
No, actually she told me, said I must have an examination. So I'm not sure why they said to you it's up to me. Actually it's not up to me. Okay, I'm not the teacher of this school. I'm the teacher of another school, so I have to follow their suggestion. Understand? It's not up to me. I don't want to get any chance at all because I need a lot of time. The result, it's a lot of time, so I don't want it actually. Because I don't have teaching assistants. If I have teaching assistants, it's okay because they can mark the score for me. But if I don't have one, I have to mark it by myself. It's quite bad.
But for us, we are in the.
But you should finish them in 2 hours, understand? And if your result is the same, if your result, the process of your result is the same, it will be treated as plagiarism. Understand? Plagiarism. So please make sure, don't give your result to other person. Okay.
I have a question. In the exam questions, did you change the number like the circuits?
What do you mean?
I mean the
number of what?
Value.
did you change the value in the circuits? The odd question?
All questions?
I mean, you give us a question.
From our homework.
So
From the homework.
Yeah. Will you change the value of the question?
I
Or
can change
you
the
do-
value of the question.
Okay.
But the reason is, if your result is the same, it will be treated as plagiarism. If your process, if I say 1 plus 1 and the second line 1 plus 2, if all the results is the same, it will be treated as plagiarism. Okay. And one more thing is, here we have some unknown value here, but the question didn't give me I1, I2, I3, okay? So if in your result you didn't mark this on the figure, for me, I will think you copy everything. Understand? So make sure everybody, if you get the result, you must mark the variable on the figure. Okay, understand? So don't copy and don't give the result to other person.
And we have some some other issue. Like we don't share this issue with the office. Like we are in the scholarship here, so we must pass our exam. And if we don't, we have to pay here a lot.
23,000.
Like 23,500
But it's not for
5 years.
I know, but
So
Miss Kong
imagine-
said, the students, they don't give me the results in paper. They give me the results by email.
Oh,
So I
okay.
don't think the examination is a closed book examination, because if you open your book and try to solve the problem, you understand?
Okay, I can understand. So it will be online exam.
It's online examination. Actually, at least for the person overseas, it will be the online examination. For you guys, I'm not sure. So I talked with her. But I don't want to come here at the moment.
Okay, so in this exam, we just take participate with 5, right?
Yeah. Just
Yes.
the 5 take the examination in school. The other person take the examination at home. Okay.
So we must come here, or we can do that from our.
I have to talk with supervisor. I'm not sure of it, because actually for previous examination, the examination is in the office. Actually, maybe it takes 2 hours of the course time, 2 hours in the course, and after the course, I get the result. But for this time, I'm not sure, because most of the guys are not here. So I'm in process with the teacher.
It's maybe from our home, because for the other class, the teachers are taking that exam. They are doing that from the home. They give the exam paper to the online, and they solve it, and they send it by email to the teacher, and the teacher marks that. That's all. So
I'm not sure, so I don't know, so I need to please her. If she said we can do this at home, it's fine. It's their time. But you still need to hang in that in time, maybe in 2 hours.
In 2 hours.
Yeah, in 2 hours.
So
You have
4 questions, right?
4 questions, and you have to submit the result in time. So if you submit maybe if the examination is started at 7, and if you didn't send the result before 9 o'clock, I won't accept it anymore. Understand? So no excuse. Alright. Okay, you finish? 1 more minute, okay. Are you happy with the result? Are you happy with the examination? I postponed it for 1 week. It should be in this week, but I'm really busy in this week. I have 10 courses today.
Wow. 10?
10. 4 in the morning, 4 in the afternoon, 2 at night.
Every day.
Wow. It's quite a lot.
I'm not happy.
How much are you select?
I'm not sure. The question is, okay, 10 courses is not a problem. The problem is I cannot talk every 10 hours, so, and I cannot stand for 10 hours a day. It's quite terrible. Do you finish?
Yeah, ma'am.
Okay, so at the time, I think the shortcut is a very useful way for us. Okay, please look at this question. After analysis, we say we can choose the mesh current method to solve this question. Okay, so we mark I1, I2, and I3 in our figure, right? And then we write our I1, I2, I3, the loop current for X, for vector X, you know? Do you remember? Here we have AX into B, right? So our X is the vector of
I1 and I2.
yes, of mesh current or loop current. Okay? Then go back to the first loop. We can see here we have two resistance inside. So here our A11 should be this one plus this one, should equal to the value of resistance in this loop. Then from here, this loop. In this loop we have two resistance, 2 plus 8 here. Here is the A22. Okay, it is the self resistance. Okay, this one self resistance of loop 1. Here self resistance of loop 2. Here self resistance of loop 3. So we can easily find in loop 3 our self resistance is 4 plus 6 plus 8, right? Okay, finish the diagonal, then we go to this triangle, right? The up triangle and the down triangle. Okay, we said this part is the neutral. Is the neutral resistance. Is it neutral?
Mutual.
Self and neutral. Self and neutral. Neutral resistance.
Mutual.
Okay, that is this one is A12 actually. A12 means it is the
Fast coincidence.
resistance connected between loop 1 and loop 2. Okay,
Yes.
so then we go back to our loop 1 and loop 2. We can see there is one consistence here.
Yes.
So the value should be
Minus.
minus a bit. Okay,
Minus.
minus a bit. The value is minus. We need
This is the rule.
that is the rule. Because the shortcut way, we concluded it from the real equation, and we find this position we have a minus here. For neutral resistance, we all have a minus before it. Okay, just for neutral, for the self is positive. Understand?
Yes, sir.
Okay, and we also have another law. Our A12 is equal to our A21.
Yes.
You know the reason? Because the resistance between loop 1 and loop 2 is the same as the resistance between loop 2 and loop 1, which means the position, the value is the same. Understand? Okay, so here, this position is our A21. That is minus 2. Okay, so then we go to A13.
It's same
We
to
find
the
loop 1 and loop 3.
4.
So it should be 4.
So minus
So
4.
A31
Is
is
also
minus
minus.
4 as well. Understand?
Yes.
Then we go to here. Here is A23. So we find loop 2 and loop 3. And it should be 8. So the value is minus 8.
Yes.
And also this one. Okay,
Yes.
so now we get the value of matrix A. So what is our matrix B? Or vector B? We
Is the
said
voltage-
the vector B is the value of
voltage source.
voltage source. Okay, so if the direction is what is that? Active. This one is active sign convention. If it satisfies the active sign convention, you can see here. We say this voltage is if it satisfies the sign convention, the positive side should be up, right? The negative sign should be down. So the value of it should be positive. Okay. Then for the 2, right? We have one control source. Okay. when we use this equation, we just treat the control source as the normal one, just the value is different, okay?
Yes.
So here we treat it as a voltage source as well. Only different thing is the value of it is not a constant. It's a function of IA. What is IA? Where is IA? IO. IO is here. It's controlled by IO. Okay. So we can see this one is still satisfy the active sign convention, right? So the value should be positive as well. The value is 10 IO. So we put the 10 IO here. Okay, here I make mistake. I
No problem.
I know. If you understand, it's not a problem. Okay. Then for the last loop, you can see there is no source inside. So there will be 0. Then we get our A and B and C. When you just solve this question, oh no, there is to be one more here. Is that if we have a control source here, we can not only just have this equation array because 1, 2, 3, and we have 4 unknown variable here. We say we should have 4 equations to solve 4 unknown things, okay? So we should add one more equation. That is the same the equation told us, right? So for IA, when we go back to the circuit, we need to find out the IA. We need to make IA equal to a function of loop current I1, I2, and I3. Okay? Then we find here IA is the current in 6 ohm, right? It is just equal to the value of I3. So we get this equation here. Then we find another extended matrix form. How to get this one? We say 1, 2, 3 is the same, right? And just put this one inside. And we can say this one 0, this one 0. Here, why it is this one is I1 because we move IA to the right hand side. It will become I3 minus IA equal to 0, right? So I3 should be 1 minus IO, so here should be minus 1, and right hand side should be 0. Then we get extended matrix format like this one. Then we can use the linear algebra. We use I. Okay, I said here we use the big I instead of this vector. Okay, so the big I is equal to the G inverse V. Okay? I think it's not a problem. What do you want to say?
I can understand last line.
This one?
Last line.
0,
0,
0, 1,
1, 1.
You don't understand this one?
Yeah.
Okay. You understand I3 minus IA equals 0.
I think minus I is 0.
Move this to here.
Oh,
Understand? And for this equation, if we write it in the matrix form or vector form, it will be I1, I2, I3, IA, right? Okay. So the coefficients of IA is 0. The coefficients of I2 is 0. The coefficient of I3 is 1. The coefficient of IA is minus 1. So the right hand side is 0. Understand? So this one is the last line. Okay? Oops. Here might be a problem because I said this one is G inverse V. But actually here I use 4 ohm. So I need to go back for here.
যদি কেউ না করে তাহলে ওরা কোনোদিন জানার কোনো ওয়ে নেই এমনি যদি তোমাকে বন্ধুর লাগে যদি পিরিত না তো দাও এর জন্য তাহলে তো জানো এনে আছে এনাকে নিজের সাথে যাবে
Just look at here. Okay, so look at here. So the equation should be I equal to R, not R inverse V. So look here, I make a writing mistake again. Sorry. You know, when you make a new PPT, you always make a lot of problems.
I wish it and I change the
Yeah, nice, nice. Okay. But it's lucky I find it, right? Okay. Next, we're going to see the general form of mesh current method. Okay. Okay. Just now we tried the practice and we did by ourselves, right? And even I didn't check this out, but I think now you understand how to do that, right? The step is write the equation, right? The first thing, write the equation, and suppose the control source is the uncontrolled source, right? Is a dependent source, is the independent source. Then write the equation. Then write another equation for the control source, for the controller, for the control signal. Okay, go back to here. So the process is, the first step, to mark the I1 to I3. Then suppose this one as the independent one and write the equation. Find the I vector, A matrix, B matrix. Okay, then write another equation for the control signal, the unknown control signal. We need to find another equation for control signal. And this equation will be in terms of the I1 to I3, in terms of the mesh current. It's not in terms of other things, in terms of the mesh current. Otherwise, we will bring a new variable, okay? Then, write the extended matrix form and try to use linear algebras to solve it. That is the normal process to solve an equation using the shortcut mesh current method. Then, we make a conclusion for the general form of mesh current method, right? If a circuit which has n node resistance circuit and only dependent source and accompanied current source, the general form of the node voltage method is as this one. Okay, so here it should be this form. Because this one is the algebra form, okay? But we can write this one into a matrix form. Can you write it into matrix form by yourself?
Yeah.
Okay. So here we take this one until this one as the vector variable of I, right? And the coefficient is the element of matrix A. The diagonal is the self-resistance, and the up triangle and the down triangle is the neutral resistance. Okay? And then on the right-hand side is the value of the voltage source. But here is the value of current source. Because in our circuit, it not only has voltage source but also current source. but we know the voltage should be this one. Okay. And we also should know the neutral resistance should be negative. Okay, this one should know this. And the self-resistance should be positive. And this one here is the sum of all current source in mesh I. The sum of all sources, voltage source of mesh I. And the voltage direction should be satisfy the active sign convention and should be rise to the asymptotic. Okay? And here, the algebraic sum of product of current source and its parallel resistance R and 1. This one we should take care of it because the R is the resistance in parallel with it. Okay?
It's node I.
Which one?
This last one. Node I.
Not R.
Node I. It's node I, but it's not
It's
number.
No, it's not node I. Here, it's not node I. It's not node I. Maybe mesh I.
Mesh like this.
Should be mesh I. Or maybe it's not mesh I, just maybe connected to this current source, you know. Because if we have a current source here, it should be like this. So here is the value of R. Okay, understand? Okay. Now we are trying to solve this practice. When you say practice, what does this mean? This means you need to try it by yourself. Okay, now we just
It looks like two system bridge. Yes.
it looks a little bit complicated. I'm not sure if you guys can solve this, but anyway, have a try.
The 5 bridge.
Yes, I see. I already marked the 1, 2, 3, 5 loops here. So it might be easy for you guys. The first step, I did it. So what is the next step? For loop 1, find the self-resistance now. Okay. Now, find the self-resistance, write it down. Okay. Use your hand. Write down the self-resistance. I know, I understand it might be a little hard for you guys to do maybe circuit analysis. It might be hard to use 2D method or mesh current method or other method or node voltage method because you need to do analysis before you write the result, right?
Yeah.
But for this method, we don't need to do any analysis. So I think this one is the method for us. So we have to try it more. Understand?
Yes.
So now all you guys write down the self-resistance for loop 1. Okay, for loop 1. Look at here. In our loop 1, it should be. Okay, write it down. Write it down. Write down a big bracket and in the position and V11 write down. Okay, then look at the loop 2. What is the self-resistance? It should be, okay, you say. Loop 2, yeah, self-resistance. What is the value? Good. Okay, for loop 3, you turn. Loop 3, you turn.
I can't think about it, that's why I can't think about it.
Okay.
Just tell me the value
Yeah.
because
Actually, it was 30 plus 20.
okay. Loop 4, you
50 plus 80.
okay. Loop 5,
20 plus 16.
Good job. Okay, so we get the value. Alright.
Which one I have to take?
Because you know how to do it, so I don't waste our time, okay? Right, so we write down those 5 in the diagonal position, right? And then we're trying to find out our neutral resistance, okay? So we have 5 loops here. So we have 1, 2, 2, 3, 3, 4, 4, 5, okay? And 1, 5. Right? Okay. Continue.
Yes, ma'am.
Please show me the neutral resistance of loop 1 and 2.
Loop and on 2.
1 and 2.
This is 1 and 2. So this is my 20, so minus 20 losses.
Good. Okay. So here A21 should be
Also
minus
minus
20 as well. Just notice here. We see this matrix, we have 2 positions it has the same value, okay? So if you calculate the up triangle, you get the value of the down triangle, right? Right now, give me the value of 2, 3, the neutral resistance of loop 2 and 3. Here. 2 and 3. Okay. Nice. Okay, please give me the value of loop 1 and 3. Here. 1 and 3. Because you say here is a big triangle, so we have many things to put them in. So what is 1, 3? The neutral resistance is 1, 3. Look at here. We can see no
0.
0 here because there is no resistance connected between those two, right? So how about 1, 4? Good. How about 1, 5?
0.
Good. How about 4, 5?
0.
Okay. How about 3, 5?
Minus 20.
Okay. How about 4, 5?
0.
Okay. The last one. Okay. Okay, we finished all of them. Okay. Then we get the value of here. Just put them directly. This one, this one, this one. Okay.
Like this.
Distribute.
0.
Distribute.
Like
What happened?
this 4, 5. And this 5, 4.
Which?
This 5, 4. This point. We have no value, so this is the 0 value.
Okay, so we miss one here.
Yeah.
Let me have a look. Here is right. Here. So we miss one here. If we have 1, 0 here, it's okay. Put right here. Okay, just tell me, okay?
I made this note.
Okay, now we're going to see another condition. We have a voltage control sources in our circuit. So just now we talked about the circuit including the current control sources. Now we're going to see if we have a voltage control sources. We have also circuits right here.
For 1 second, can you just go back this page?
Here.
Okay.
Copy that. It's at page 50.
Yeah.
page 50. Okay.
50.
Right here. Now we're going to talk about a circuit which has voltage control sources inside. There are two cases. The one is voltage controlled voltage source, another one is voltage controlled current source. Right? Okay, let me have a look at this one. If we control a voltage controlled voltage source, the first step, we treat it as an independent voltage source and write a KVL equation for the meshes. So this part is actually more like a conclusion, right? It's more like a conclusion. So the first step, we treat it as an independent voltage source and write our KVL equation for meshes. And then we express the controlling current in terms of mesh current. Because the controlling voltage is a unknown variable. And if we want to solve this one, we need to add one more equation, which is in terms of the mesh current. Then we can solve the equation area. The case 2, we have a voltage controlled current source here. The first step is the same. We treat it is like an independent source. But here, because we will write KVL equation, right? KVL equation, we need to know the value of V. But actually the value of V is unknown because it is a current source, right? We just know the current of it. So we just suppose we have a V here, right? And we use this V to write a KVL equation. And then the step 2 is the same as this one. We write equation for Vx because Vx is unknown. Understand? Write out Vx in terms of KVL equation and add one more constraint equation for the V. No, it's not Vx, it's V. Okay? For the V here. Because we introduce a V. V is unknown, so we should add one more equation. Right? So anytime when we want to solve a circuit problem, it is actually a mathematical equation. For mathematical equation, we know if you have n unknown variable, you should have n equation. When you introduce one new unknown variable, you should introduce one more constraint equation. Okay.
What is independent source?
Independent source,
Yes.
just circuit.
Yeah.
Just treat it as an independent circuit.
Really? Is this independent source?
No, it's not independent. The treat is like just in your mind. Suppose it's a circle, a circle here.
Yeah.
Okay, and if it's a circle, you must can write out the KVL equation, right? If it's an independent one, can you write out the KVL equation? Yes, right? But actually, when you write out this equation, you will find if it is a independent source, it should be a voltage source, right? But actually, this one is not. It's a voltage source.
Yes.
So we should suppose the voltage of this independent source is V. Just suppose it. Okay, and then find out the relationship between the real one and the visual one. Find out the relationship between them and we get the result. Understand? Okay, and here I mark the direction of I here. You can see here. I1 clockwise, I2 counterclockwise, and here is also the same. So here I3, here I4. Let me have a look. I'm definitely sure those two equations, one of those two equations is wrong. I think this one is Vx, but this one is V. Because the value is here, this one should be V. Let me have a look. I3 minus I4.
Like I1 minus I2.
I1 minus I2. This one is go well. This one will go back to the equation. This one is right.
And also, these times are resistance.
What?
Here. And V equal I3 minus I4 times
D?
dx.
dx, yeah.
Fine.
This one is right.
No R.
But this one,
It's not right.
this one should be V.
Yeah.
V here. But actually V is the voltage. So this equation might be wrong.
Because no resistance.
Yeah, this equation might be wrong.
Because
But actually we need to find out the V here. Our V should be, what is the variable V? Because here it's current. Current is not the variable V. Definitely not. Because it's supposed to be here. So we need to add one. This is in parallel to this problem. Okay, anyway. We might see some example here. What is the value just now? Okay, just let us see this example.
okay.
Do we have, let's see this example and we'll find out the result. Voltage control voltage source. Is it voltage control current source? No.
It's current from the current source.
This current control current source. This one is voltage control voltage source. So we need voltage control current source. Do we have? No? No, I don't have one here. This one is current control current source. But now we need a voltage control voltage source. Do we have voltage control voltage source example? This one is current control voltage source. This one is voltage control voltage source. But we need a voltage control current source for example. Yeah, this is voltage control current source.
This is infinity. This maximum power.
So our one equation, two equation,
Another side also. I find this P max also, that's why this is wrong. But you can find this.
V0, V1 is equal to V0, V0 is not here. But you didn't use the same way, you know. You didn't use the same way, but for this method, we suppose the V and write it KVL notation, and then we should get the value of Vx and V. Here we just get Vx here, but for V, I think this equation I make a mistake here, because I3 minus I4 is not equal to V.
Yeah.
Because V is the voltage we suppose. So for this case,
Because the current difference is not equal to the voltage.
So for this equation, it must be wrong. But what the correct value, I'm not sure. I think,
I have another reference. This is voltage controller transport. This one.
it's current control current.
The two circuits. Oh, this one.
equation is right as well. But I just don't know where is my V. V is gone. Okay, anyway, when I go back home, I'll have a check of this one. This equation is right, and this equation is right as well, but just has no relationship of V.
My question is, there is no resistance.
Which one?
We know V equal IR. So here V equal I equal
V is
I3 minus
V is not
I4.
equal to IR here because here we don't have R here. We don't have IR here. So
So Vx equal V.
V is not equal to Vx.
So Vx is the current difference.
V is the current, V is the voltage of this current source.
So Vx.
Between those two is the V.
Hmm.
But the current is Vx.
Oh.
So Vx should be equal to I3 minus I4. So this question is right. And this question is right as well.
Yes.
Just V. So where is our value of V?
Yes, sir.
So you know what the problem? So because I write out maybe a trivial equation array, and in this equation array we have the current I1, I2, I3, I4 maybe, but I didn't use the equation which can give the relationship between I and V. That's my problem. So I need to check about this. Okay, let us have a look at this example. Here, we are trying to use the shortcut way as well. Just have a try. Please.
No.
Just imagine if we take this part, move this part, if we remove this part and put another voltage control current source here. Okay. So and we also can suppose if we put one like this, Vx and voltage control current source here. Okay. And suppose the voltage of it is V, right?
Yeah.
For this case. So we can find the V from this loop. Understand?
Hmm.
So the V in this loop, the V should be I4 times this one.
Yes.
So that equation is right, but I didn't write down the equation here. So for here, I think we should add one more constraint equation for voltage source and matter sources, but we cannot do the general form of this one,
Okay.
right? Okay. Just look at the example, and now trying to use the shortcut way.
No, for me, but I think this node voltage is okay because it's two nodes. I find.
Yes, but now we're trying to use shortcut way. Okay, this shortcut way is very quick.
Yes, sir.
Okay, try. Here we put 1, 2, 3, 4 meshes here. Actually, we have shortcut way for mesh current method. We also have shortcut way for node voltage method as well. Remember?
Yes.
Okay. So actually for this case, 1, 2, 3. Okay, for this case actually, I think for node use the shortcut way for node voltage is more easier.
Yes.
And here, our purpose is trying to familiar with the shortcut of mesh current method. So we have tried this one. Okay. you. Right. So now, what is our vector of I? Vector of I, the red one. You can see we have 4 meshes, right? So we have 4 elements in our vector of I. It should be 1, 2, 3, 4. Okay, easy? Easy? There we have 4 circles, and here we have 4 elements of I. Easy? And put this element in the vector of I. Just follow the direction 1, 2, 3, 4. Okay, and then we're trying to find out the diagonal value, the self-resistance, right? Okay, the first one, A11, please. What is the self-resistance of loop 1? Loop 1. Go back to loop 1. What is the value? A11. The self-resistance of loop 1. Good. Okay, for you.
Second,
Loop 2.
loop 2 is 2 plus H.
Okay, for you. Loop 3.
8 plus 4.
Okay. 8 plus 4.
4 plus 1.
Okay, you. Loop.
1 plus 2.
Okay, good. Okay, now we're trying to find out the up diagonal, okay? So, for 1 and 2, give me the value. 1 and 2, look 1 and 2. What is the value? What is the value? Tell me.
Minus 2.
Okay, good. Okay, for 1 and 3, yeah. 1 and 3, 0.
No connection.
Yeah, 0. For 1 and 4, you.
1, 4.
1 and 4.
1 4.
Minus
1 and 4. Where is minus 3?
1,
Look 1 and look 4. Where is just
zero.
almost. So what is value? What is value? The neutral for look 1 and 4. Just be brave. Tell me your result. 1 is here, 4 is there. So what is the thing between them?
or between them, no zero.
Good. Okay, so how about 2 and 3?
2 and 3.
Good. How about 2 and 4?
2 and 4.
Minus 2.
Good. How about 3 and 4?
3 and 4
And 0.
Okay, so then find out the up triangle and you get the down triangle. Okay, so do you know, I'm not sure if you know, for a matrix A, you know for a matrix A, the value inside is A11 to small a n. Okay, so this one, Aij, okay, A goes this way, J for this way. Understand? Make sure you remember this, okay? I for row, G for column. Okay? No. Column is this one. Okay. So column is this one? Column is this.
Yes.
Row is this. Okay. So I for row, J for column. Remember, okay? I always make the confusion about this two.
Yes, every time.
I can tell you the reason. Because when the first one I learned English, I always think, okay, this one is row. The actually this one
It's
is row.
It's
It's row. Okay. Do you have any easy way to remember this?
No, we also forget it every time.
This one is row. This one is row.
I have my teacher tell me, this is the row, this is the column. This is the row, this is column. This is the row, this is the column. Like, this is my matrix. Take this way. And see, this is the column, this is the row.
This thing here is row, and this one is column.
Okay, just let me think.
Okay, you can also do like this version. This is my column.
I think it may be a better way for me just to remember one.
Yes.
Don't try to remember two. Okay, this one is row. I just remember row. Another one is column.
This is the row.
Okay.
And this is the column.
Okay, I need to.
This horizontal
okay.
is row.
Okay, I have a better way to remember this. Every row is going to row. Okay, so row is this direction.
This is the column.
What?
Yeah.
No,
This
it's
is
row.
No, this is column.
This column.
Yeah. This is the row.
Okay.
This is the row. Also. This is the column.
Okay.
The column is always like triangle, like 90 degree of row. So this is the row, and this is the column. Not this is the row, and this is the column. this is the row.
This is the big tabby.
Okay.
And the corner side is.
In my mind, when I first learned it, I think this is row.
Yeah.
In my mind, this is row. So when I find out I make this mistake, it's really hard to change. It's really hard to change. But every time when I say row and column, I definitely know I might make a mistake. Okay. Anyway. Okay. When we finish the A, and then we're trying to finish the B. So going to the loop 1, here is independent voltage source. I'll just write the value down, okay? To satisfy the positive sign convention, and then loop 2. Here, this one. What is this? It's a controlled voltage source, right? So, we're just supposed to be independent one. But this one is still a voltage source, so we just write the values, leave the 0 down directly here. And for loop 3, there's no voltage source, so it's 0. So for this loop, again, suppose this one is independent one, and write down the value of it. But here we find there is unknown variable B0, so we should give another equation, a supplementary equation for this controller signal. B0. So it's here because B0, the value is here, so we can find the voltage current relationship between, for this system, the Ohm's law, right?
Yes.
Okay, so for Ohm's law we have B0 equal to 4I3. So we can easily find B0 is the equation of loop current, right? Then we can write down this equation in just put back this equation inside. And when we put back this equation inside, this one will be changed. But it's actually not this one. Why? Because I removed this one and this one to this part, to the A matrix. The red one, okay? I removed it from here. Because this one is 12I2 here. When we put this one inside, is it? When you're trying to put this one, put back here, it will be 12I3. It should be 12I3 here, and here will be minus 12I3. And we're trying to remove this one to this side. Can we?
Oh, yes.
Just minus the coefficient, okay? Because this one is I3, so the coefficient of A23 will be changed. Understand? Move this one from here to here because the value of the coefficients of I1, I2 is not changed. Of I4 is not changed as well. Just change the value of I3. Okay? And here the same. And then we have 1, 2, 3, 4, 4 equations for 4 unknown variable 1, 2, 3. And we get the value. This one. I1, I2, I3, I4. But this one is not the branch current value. What is it? It is the loop current value, right? For example, for this one, the branch current I is equal to loop current I1 minus loop current I2. So, we get this equation. We put the value of I2 and I3 inside, we get the small I1, the branch current. The same, we can find out the branch current I2 and I3. I2 is equal to I2 minus I3, right? I3 equal to I3. Right? So, we get this one. And we finish this problem. We find out the branch current. Okay, now we are going to see another example as well. Here is the current source. We have a I1 here, so the controller is I1. I1 is here. So this one is current source, current control current source. And put the reference signal here. Here is another method, I think. This method is node voltage method. The shortcut of node voltage method.
Yes.
Okay, so for node voltage method, the first step, we select a reference node. So, generally, which node will be selected as the reference node? Generally, I select the node which has more current connected to it as a reference node. Okay? Or which has more branches connected to it, and I select it as reference node. Then the next one, select the node voltage V1 and the node voltage V2. Okay, so now our variable vector will be small v1 and small v2. Actually, okay, here is small v1, here is small v2. And then we need to write out the self what? Conductance, right? So for self-conductance for this node, the self-conductance is the conductance connected directly to it. So it should be 1 over 4, 1 over 1, and 1 over 2, right? And for node 2, it should be 1 over 4 and 1 over 2. Okay, and between this node and this node, you can see it should be this one, right? So it's
minus 1 over 4.
Minus 1 over 4. And it's G1, 2 is equal to G2, 1 because it's symmetric. Okay? Right? Then we get the G matrix. This one is the G matrix, right?
Yes.
And then for the right hand side, it should be the value of current source. So for node A, the current source
5 is coming, and
we have a current source here, right? It should be when it's going out is negative. When it's going inside, it's positive. Remember? So here is minus 2. And for this part,
5 ampere is coming. 10 over
yes,
2.
and here is coming, so it's 10 over 2.
2 minus 2.
Yeah, so it's 10 over 2. What is the reason? Why is 10 over 2?
Because this from
Because
borders.
For this one, we can change it to another form, right?
Yeah.
For both connection in series with resistance can be converted to counter source in
A
parallel
parallel of
with
this resistance.
resistance.
It's Thevenin to
So the value is, for example, this one is B, this one is R.
Yes.
So if we want to make this transfer, the value of R is still the same.
So
But
current is
I
zero.
is equal to V over R. This one is Savani and Norton's theorem.
Yes, ma'am.
Okay.
That's formula.
Okay, the next step, and we need to find out the value of I2. I2 should be an equation of V1 and V2, right? So when we try to find I2, you see I1 is here. Is controlled by what? Here, by this one. So we go back to this way. Go back to this branch. For this branch, we know the voltage difference is V1 minus V2, right? So the current should be V1 minus V2 over 4. Easy? Easy? Okay. Then we put this one back to this equation. Anyone, and everybody, we should know when we find out the relationship. If we want to use maybe an easy way, maybe this algebra, linear algebra, we need to put it back into our normal original equation and then find out the extension or another one. Maybe you can see here. We put this back here. Okay, so this part here is changed. We have V1 and V2 here. But we still need to remove this part to the left hand side because we want all of the coefficients of the variable is on the left hand side. For the right hand side, we just want to see constant. Easy? Okay, so here the coefficient is 1 over 4 and then minus 1 over 4. Okay, because here the sign is minus. When we remove it to the left hand side, it will become plus, right? So it should be 1 over 4 minus 1 over 4 plus 1 over 4 V2. It should be this one and this one. Let me have a look. Yeah. Here minus. When we go back here, it's positive.
Positive and positive will be
Positive
negative.
minus.
Yes.
Positive V1 minus V2. Easy? Okay, our step 2. See, we have this equation. Now this equation is right. It's lucky, right? So, our V will be this one. Just use maybe, you can use your calculator or you also can use MATLAB and you also can solve it by your hand because this one is a 2 times 2 matrix, right? So it is easy to solve. Still remember the diagonal minus inverse diagonal. Remember the product of inverse diagonal. Product of diagonal minus the product of inverse diagonal. Okay? And you get that. Right? Step 4. When we get the node voltage value, we know node voltage is the variable we solve and to make our calculation easy. But it's not the real value we want, right? The real value we want is the branch current. I1, I2, I3. So we still need to calculate I1, I2, I3. So our I1, we know, for this one, we can write out the VCR equation, V1 minus V2 over 4. We get this one. And for I2, here, I2 is equal to V1 minus V0 over 1. And for I3, where's I3? Here. It's equal to V2 minus V0 over 2. Our V0 is 0 here. So we got those equations and just solve it. And we easily get the result. Easy? Got it?
Not exact. next we did one. Step 3 again, please.
Which one?
Step 3.
X3.
No, step 3. B equals G minus.
No, step 3.
Step 3.
Step 3.
Yeah.
Yeah. V equals to G inverse I.
1.
GB equals to I. What is G? G
One
is
by one.
here. G, V equals to I. And inverse this one times the inverse G1 here. G, V equals I. And inverse G here and inverse G here is the same. Understand? And this one will become I, identity matrix. So I times V equal V equal G inverse I. Easy? Got it? Okay, now we're going to see the conclusion. In this part, it told us which way or which method we should select when we got a problem. In principle, both the nodal analysis and mesh analysis is the useful way. But when there are two factors that dictate the best choice. The first one is the nature of the particular network is the first factor. The second one is the information required. What does this mean? The information required means the information is given us. It's given to us. It is known things, right? We care about the known things, and we care about the topology of the circuit. Topology. You know topology?
Yeah.
We know for topology, we know how many nodes we have, and we know how many meshes we have, and how many loops we have. So from the topology, we know which might be the best way to solve it. Because we know the value of n, and we know the value of b, and also l. Okay? So, we do mesh analysis when the network contains many series connected elements, and it contains voltage sources. It contains more voltage sources, and it contains super meshes. And a circuit with fewer meshes than nodes. For this kind of thing, for this kind of circuit, we prefer to use mesh analysis. And if branch or mesh current, we are going to solve the branch current or mesh current. This way is better, because the branch current is the variable we get. Understand?
Yeah.
Okay. If we use another method, we need to write out another equation in terms of that, right? The third mesh analysis is only suitable analysis for transitory circuit. Do you know transitory circuits? No, actually, right?
Transistor circuit.
Yes. For that circuit, we might use the mesh analysis. That's the nice better, because the node voltage we cannot see the node voltage inside the transistor, right? So we just can use mesh. It is not a portrait for operational amplifier. What does this mean? You know operational amplifier?
Yes.
Okay, so it's not suited for that because there is no direct way to obtain the voltage across it. It's still like black box, we don't know that, right?
The operational amplifier.
And operation amplifier
The chapter 5.
is like this, right? And we don't know.
This chapter 5 is zero.
Yes, for that one, maybe we'll just know the voltage on every port, right? We don't know the current inside.
No current is inside. Current is 0, but 2 voltage is inside.
Yes. Okay, we do nodal analysis if the circuit contains many parallel connected elements, and we are prefer to use nodal analysis. More parallel connected elements means more nodes, right? Okay, and we have more current sources inside, and we have more supernodes inside. And there are fewer nodes than meshes, and in that way, we should prefer to use nodal analysis. If node voltages we are going to solve, we also choose the nodal analysis. It is more easier. Okay, and we should notice a non-planar circuit cannot only be solved by using nodal analysis. Do you know non-planar circuit?
Planar, non-planar.
Planar circuit means the normal one is planar circuit, but the non-planar in our mesh group, many circuits is non-planar. Okay, there are many circuits that are non-planar. That means if we change the position of node, it's still cross, has some cross.
Oh, I remember
Change. If you change for some circuit, if you change the direction and you can put them in a 2D dimension circuit, right? Figure, right? But for something you cannot. It's always 3D. It's always 3D. Okay, this format is easier to solve by computer, the nodal analysis. I think both of them are easy to be solved by computer, right? Computer is our best friend.
He is also my special.
Okay, here is the conclusion for this chapter. And for node voltages, here are some
This
conclusions.
is planar or not planar? This 3D.
It's regarding to
This all is R.
is non-planar.
This is 3D, like a cube.
It's non-planar.
Non-planar.
Okay. Here is the conclusion. For node voltages, there are 4 conditions, right? So when we see when we see fewer nodes, when we see planar, and when we see more current source, and when we see more parallel elements, we prefer to use the node voltage method. And in constraint, if we have fewer meshes and it's non-planar circuit, and if we have more voltage sources and more series elements, we prefer to use mesh current, right?
Yes, sir.
So, here, please notice, this one is the first condition. So, most of the case, when we see if it's fewer nodes, just choose this one. If there are fewer meshes, just choose this one. Okay? But we should notice, because in most of our case, it's all planar circuits, right? So, we don't have non-planar circuit in our practice, actually. And current source and voltage source, because the current source can be transferred into a voltage source, so I don't think it's a problem, okay? And here, more parallel elements, it is also not a problem, I think. Because you can do circuit simplification. You have got the equivalent circuit, right? When you do circuit simplification, everything is easy, right? Okay, for this case, we analysis unaccompanied voltage sources. Do you know what is unaccompanied voltage sources?
No.
Okay, we say this one is voltage source, right?
Yes.
And if it's just connected between 2 nodes, we say this one is unaccompanied voltage source, because it doesn't have the resistance in series with it. If it has this one, it's accompanied. If it doesn't have it, it's unaccompanied. Okay? And this one, for this case, it will be treated like a supernode. What does this mean? we take a big circle and put this one inside. And this one is treated like a big supernode. Just take this one as a node. Okay? Put a very, very big circle and this one inside, and take this one as a supernode. You know supernode?
Yes, ma'am.
Okay. And then we have dependent current source and dependent voltage source. Remember? For this kind of case, we always treat it as independent one and trying to write out KVL equation, right? And then add one more or two more controller constraint equation. And then we get a result, right, for this one. And for dependent voltage source, we need to assume I, because here our variable is branch current. It's not voltage. It's not voltage. And we need to write out the node voltage using the I. And we also has treated as independent and has controller constraint equation as well. And one more thing is we have the source constraint equation for this one. For the I, we assume. We have the source constraint equation. That's the difference. Only add one more equation, just because we assume one I here. So let me have a look. Node voltage, we have V1 and V2, and the equation is use V1 and then V2 and write KCL equation, right? Okay, for KCL equation, we need to know the I. So the I will become one thing in the right hand part, right? Or left hand part?
Right.
Right hand part, no voltage. Yes, right hand part, inside B, where we are I. But we also need to write I in terms of V1 and V2. Okay, so for this one, we use, for node voltage we have V1 and V2, right? And then we need use this one to write a KCL equation. Okay, and for this one, we have I1 and I2. Okay, we need to use this one to write a KVL equation. Okay, it's different. Right, here we also have accompanied voltage sources. That's the normal one. We can use the Venn equivalent to make it become the accompanied current source. Okay, because here we use KCL, right? So we need a current source. We don't want a voltage source. But here, if we have a voltage source like this one, so we can transfer it into current source. Then, for KCL, it's always something like this, right? So we want to know I1, maybe, so we just want I, and I, and I. Okay, I1, I1, I2, I3, right? But we need to write this one in terms of V1 and V2, this one in terms of V1 and V2, this one is in terms of V1 and V2 as well. Just remember. Okay, so you should remember it by heart. For node voltage method, we have node voltage V1, and our equation must be an equation of V1 and V2. But for V1 and V2, we need to write another KCL equation. Okay, we need to write the equation of KCL. For node, okay, for node, we write KCL equation. Okay, the equation is for node, but the variable is for node voltage. Remember? Okay, so the first word is the equation type. If it is not, we write KCL. If it's mesh, we write KV there. But we also see it's voltage. So we need to write an equation of voltage. Here we need to write an equation of current. Okay? Okay, for the mesh current method, we also have some other cases. The first case is unaccompanied current sources. What is this? Unaccompanied current sources. Here we have two nodes as well. And we have voltage here. We have a current source here. Okay, so unaccompanied means just this one. Unaccompanied means we have a resistance and parallel resistance. Have this one is accompanied. Know this one unaccompanied. For unaccompanied means this can be treated as a super mesh. What does this mean? You know super mesh?
Yes.
Super node, super mesh. I forgot how to say this one in Chinese. This one is